So hello everyone and welcome to this next lecture. So in this lecture I'm going to continue with the Cuk converter that I started last time, and in the last time I had actually just set up the simulation and I had drawn the circuit. Alright, so I will continue with this lecture. So before I get started, of course, a little bit of background that if you are interested in these kind of lectures but you find these video lectures to be a little too light, I do have a comprehensive course on simulation on the online website called Udemy. This course has almost the entire process of simulation, including how to install the software, how to run the software, a little bit of theory, and also an entire case on how to simulate a buck converter. So if you are interested in online learning but you want something more comprehensive, please do check out the course. The link for this course is provided in the description for this video. And if you are interested in simulations but you do not have the time for watching video lectures or for an entire course, this link here is of my Gumroad account where I upload simulation files, and if you want the simulations you can just download them and try it out. So these are options. Both these links are provided in the description for this video, so go ahead and check them out if you want additional resources. So now I'll continue with this lecture. So first thing we have to do is let's go back to the circuit, and I realized I made a mistake, or rather I didn't really make a mistake. I forgot to add one thing. So we already talked about how the circuit is built. That is, we have two inductors. We have an input inductor and we have an output inductor, and we have a decoupling capacitor in the middle, and therefore this decoupling capacitor plays the role of taking energy from the source and transferring energy to the output. So the only thing I forgot is we should measure the voltage across this as well. So let's connect something. So we could simply connect. All I have to do is insert a couple of elements. You can do this in any way you want. I just prefer this, and we need to add it here as well, and let's insert a couple of them here as well. And we need to add them here. So we have completed this. All we have to do is add the voltmeter here. And let's call the voltmeter C1 just to make it compatible with this entire branch. So we now have a voltmeter across this. So let's save it again. So we are now going to add this circuit into our simulation in this lecture. Let's do so. So we have already edited the circuit parameters. We added the directory. This directory, as I said in the file browser, we created last time, where we are now going to put all the files for the Cuk converter. So let's go back to the main page and let's add the circuit. So we go to add circuit file. Here we just have to choose. First we have to go to the Cuk converter, and then we have to choose a circuit file. So we'll just say converter circuit, save the file. So we are done. Now let's process the circuit schematic. And the circuit does not have any detectable errors. So this circuit is acceptable as for now. We can go ahead and edit the parameters. So let's do that in this lecture as well. So there's only one circuit. We see that here. We just have to view components, and the components will have default parameters. So we just have to change them. So let's go back and change them one after the other. So first is the ammeter, which is C1. Let's go over to the circuit. This is the ammeter C1. Now, as I said, in this converter, when the switch is on, the input will charge the inductor through the switch. At the same time, the capacitor is going to discharge through the switch in this, I would say, in the anti-clockwise direction, and will charge the output and the inductor, right? So this is how it works. So therefore, the direction of the current in the capacitor will be in this way. When the switch is off, the current, the input, and the energy in the inductor will be used to charge the capacitor and will flow through the diode. At the same time, the current in the inductor will continue to freewheel through the diode in the anti-clockwise direction and will continue to charge the capacitor. And the capacitor, of course, will be feeding the load. So, what this means is the current in this capacitor will be reversing, which means in one case it will be flowing in this towards the left, and in the other case it will be flowing towards the right, because in one case the capacitor is discharging, in the other case the capacitor is charging. So really speaking, we can give it any direction we want. Let us give it the direction towards the right, because we say let us see that it charges. So if it is 1 end, let's give it 1 ohm. And we change this to 1 ohm. And we'll save it. The next one is C out. C out should be fairly simple because C out is here. The ammeter C out is basically, again, just like the buck boost converter, the Cuk converter has a negative polarity. So it's actually the capacitor, the positive polarity is downwards. So what that means is the current in this capacitor is entering from the bottom. So it's moving, the direction of current in this branch is bottom to top. Now we can maintain that, but I would strongly still maintain the polarity of the output voltage to be still positive, because we want to show that the output voltage is negative, but the current in the capacitor is okay. So let's give it a direction in the upward direction. So the polarity is at 11 AA and the direction is 10 AA, which means it is in the upward direction. It can stay as it is. So now the current ammeter D1, let's go back and have a look. So the ammeter D1 is this direction. Now, as I said, when the switch is turned on, the diode doesn't conduct, because both the input and the capacitor are discharging through the diode. When the switch is off, that is when this diode is going to conduct, because now the input and the inductor are going to discharge through this capacitor, which is going to now flow into the diode. At the same time, the inductor current will also freewheel through the diode. So both of these will go. So let's look at the direction. If the direction of current of the inductor is in the clockwise direction when the switch is turned on, this direction will continue to remain in this direction. So the current will flow in the right. If the current flows in the right through the capacitor, it has to flow downwards through the diode. It cannot flow anywhere else. Similarly, when this inductor is being charged, when this inductor is charged, when this switch is on. So for example, the capacitor discharges through the switch and charges the inductor, which means the current through the inductor is flowing towards the left, that is inductor L2. As the current through the inductor is flowing towards the left, when the switch is turned off, it will continue to flow towards the left and it will flow down through the diode. So both the capacitor and the inductor will push their currents through the diode downwards. So this current ammeter D1 should be downwards. So let's do that. So it's ammeter D1, position is 11S and direction, positive direction is 10S, which is wrong. So we have to move this to 12S. So now that D1 is done, let's look at L1. L1 is pretty simple. L1 is here. We know already that the current is going to flow in the clockwise direction, and that means this ammeter, the positive direction is towards the right. So we have, oh sorry, not L1, it is this L1. So it's 1C, again it's also towards the right. Actually we can delete one of them, but doesn't really matter. We can leave it as it is because it's 1C and the positive direction is 1D, which is towards the right. Let's look at L2. L2 is here. As I said, the current in this inductor will be flowing towards the left. So therefore, this ammeter L2, the positive direction is towards the left. So the component is at position 1W and the positive direction is towards 1V, which is exactly as we want. So we can leave it as it is. Now look at the ammeter. The ammeter I in is this one. This is the input current, and just like the ammeter L1, the current in this branch is going to be flowing towards the right, which means the positive direction is towards 1B. Let's do that, and it's already 1B. We don't have to change it. The last is the load. This is the load current. Here once again, even though we know that this capacitor is actually being charged in the negative polarity, so the positive polarity is down, it would still be advisable to keep our output voltage and our load current to still be pointing downwards, because we want to still show that they are actually negative. So therefore the ammeter load will be downwards. So we just have to go change that. Ammeter load is 5 AC and positive direction 4 AC, which is upwards. Let's change this to downwards. And this is done. So this with this, the ammeters are done. Let's look at the capacitor. So first is the capacitor C1. Now this capacitor C1 need not be as large as this capacitor Cout, because Cout is the output capacitor and this is the output stabilizing capacitor. So this forms the output bridge, or you can say the output bus. So this needs to be large. It needs to be way above, maybe 500 to 1000 microfarad. But this capacitor C1 need not be that big, but still it has to be large. The reason is, this is actually an energy decoupling capacitor. This is not a filter capacitor. So this does take a significant amount of energy from the input and transfers it to the output. So we do need some amount of size here. So what I would say is, I would make this capacitor around 100 microfarad. And the polarity doesn't, as I said, polarity doesn't really matter, because this is more for debugging purposes. We'll just leave it as it is. It is towards the left. That's not a problem. Let's save the parameters. So with this, C1 is done. And as I said, now we come to Cout. Cout is indeed a large capacitor, because this forms the output bus and we need a steady constant output voltage. For that purpose, let us have something significantly large. Let's make it 500 microfarad. You could of course increase this to 1000 if you want. That's always possible, because it is acceptable to have large capacitor output capacitors if you want a steady voltage. So now the diode. The diode is this one. Now we are going to use this Cuk capacitor. Let's use the Cuk converter for 12 volts. So since we are using it for 12 volts, a voltage level of 120 volt is quite okay, because we have a voltage level that's, I would say, almost 10 times more than the input voltage. So even if we have a boost ratio of around 2 or 3, we are still we have a huge margin between the maximum voltage. This can remain as it is. The most important thing is the polarity. Now, as I said, the current in this diode, both the capacitor and the inductor are going to push current downwards. So what that means is the cathode has to be below the component. The cathode has to be pointing downwards. So the component position is 7S. The direction of cathode is 6S. This is wrong. We need to reverse it. So let's change this. So this has to be 8S. And this is done. Now we have the inductors. Now there are two inductors, L1, L2. We can start with 1 millihenry. Typically they would be a little lesser, because that is the advantage of a Cuk converter, that since we have two inductors, the sizes of the inductors are lesser. But for our purposes, in just a starter simulation, this is good enough. We are not doing an actual product design. This is good enough for us. Now the resistor. The resistor, as we know of C1, is this parasitic resistor of the capacitor, because every branch must have some resistance. So this should be very small. Let's decrease this from 100 ohm to, I would say, around 0.20 milliohms. This is quite okay. You can always change this, increases a bit, decreases a bit, depending on how much loss you want to bring into the system. And same for Cout. Because they are also parasitic resistances. And of course there is also another one, which is R1. R1 is the parasitic resistance of this inductor, that is also on the same magnitude. You can increase it a little because an inductor usually has a little more loss than a capacitor, so you can make it 0.1. So with this we are done. We have, oh, I'm surprised it did not change. Let me do it again. Oh, I think I changed the load resistance. That was a mistake. I see that has changed. So this is R1, and the next one, the load we can make it around 10. It's quite normal. You can decrease this to 1 or 2 if you want a high load. You want it for, because it's like this. We have, let's say, an input voltage of 12 volts, which is a sample like a car battery. Even if we do not boost it up or boost it down, so it has, let's say, we are just transferring it, which means the output voltage is also 12. 1 watt would mean that it is 12 watts. So if we have 10 ohms, that means we have a little more than 1 watt, maybe 2 watt or 3 watt, which is quite okay. And finally, we come to the switch. The switch is a very, very important component. It almost always needs editing. The rated voltage levels can also be 120 volts because, like I said, we will be taking a 12 volt input voltage, so that's 10 times more good enough. Now, the polarity. Let's go over to the circuit. The current is going to flow in the clockwise direction. So when the switch is turned on, the current is going to flow in the clockwise direction. So through the switch, it's going to flow downwards, which means the negative polarity of the switch has to be pointing downwards. And it is pointing upwards because the component position is at 8F and the negative polarity is at 7F. So we have to reverse this. 9F. Now, the gate tag. The control tag for the gate is best to be given as the total name of the component. So what I would do is call this switch S1. Right? So you can name it even with the underscore, or you can remove it either way. I would it would be more convenient to remove underscores for when it's not really needed. And we are more or less set. There's nothing more to be done. The only thing is the control tag is a unique identifier of that particular element. So it's the simplest thing you can do is give it the same name as the element. You can think of another also unique name if you want, but the name of the element is always unique, so that's good enough. The voltage source. The voltage source is usually an AC voltage source, and that will have to change. So we make this 0, frequency is 0, the DC offset is 12 volts, and the polarity. The polarity, we would like this to be upwards. So the positive polarity is upwards because the Cuk converter will produce a negative voltage. So the output, the voltage, positive polarity will be downwards. So let's make this upwards, and it already is upwards. The component position is at 8A and the positive polarity is 7A. So this is already done. So we just have to save it. And we go down again. The last is the voltmeter. First is the voltmeter across the capacitor. So now, as before, this capacitor will actually be charging and discharging. But if you look at the way you would expect it, when the switch is turned off, this voltage will be charging, and the inductor, input and inductor will be charging the capacitor. So the current is going to flow towards the right. This capacitor, in most likelihood, will have a positive polarity towards the right. So therefore, voltmeter C1 can be measuring a voltage such that the positive polarity is towards the left. So let's do that. The voltmeter C1, let me edit this. The component position is at 5L and positive direction is at 5K. So positive component position is at 5L, positive polarity is 5K, which is exactly the way we want. We don't have to do anything. Just save it. And the rated level can also be 120 volts because, like I said, we are going to choose our input voltage to be 12 volts. All of them can be 120 volts. And the last. Now, here, as I said, even though the Cuk converter produces a negative output, we would still want to show that the voltage is negative, which means we are going to have a voltmeter which is still measuring an output voltage that has positive polarity upwards. So the component positive polarity should be upwards. Let's do that. The component position is at 8 AE and the positive polarity is 7 AE, which is exactly what we want. So we don't have to edit this at all. So with this, we are done with editing the parameters of this circuit. So this lecture has gone long enough. I will stop this lecture now. If you have any doubts, please do post in the comment section and I'll be happy to help you out. Otherwise, just email me or message me on social media or whatever you prefer. I'll be happy to help you out if I do see those messages. So thank you so much and see you next week, where we will be continuing with this, where we'll be setting up a basic control strategy, or rather an open loop strategy. We'll be just copying over our PWM from the previous lectures. So see you next week. Thank you so much. Goodbye for now.